control, so it's not an autonomous system. But later on, you can worry about how to replace the human driver by a computer, so then you will have an autonomous vehicle, right? Some terminology, the object which we need to control is called a plant. The plant. Yeah. So this is the car. The controller is the driver. So those are the very basic terms we use in control. So you probably have heard about open loop control, closed loop control, or feedback control, all those concepts. What do you mean by open loop control? Assume that this driver is so smart that he doesn't really need to. He doesn't really need to look at the environment. He doesn't really need to see anything. He just he can drive the car with eyes closed. Right? Basically, he can compute what he needs to do in advance. Right? If that's the case, we say it's open loop control. There's no feedback. You don't need to do observation. Well, it's easy to imagine that this is, it's not going to do a good job. You won't be able to precisely compute everything at once. Especially you have uncertainty. You don't know what the wind direction that day. You cannot predict that road condition. So open loop control is something used occasionally by people in industry, but it's I don't suggest it. So it's basically impossible to do anything good. So later on, when we talk about control, we always mean closed loop control. Yeah, in closed loop control, this driver has to see, just see what is the real position of your car and make adjustment according to your observation. Right? So you basically look at the outcome, and then you decide your control action using your observed outcome. So this is the information actually goes around the loop. Right? So then so for the feedback control. Well, feedback control makes sense. Right? We should be able to control the system. We should be able to control this system. We should be able to stabilize it. Okay, more abstraction. So we have plants. That's a car. We often use a block diagram to depict the control system. So in the control system, no matter how complicated, you have those blocks. You have those arrows, these signals, to connect those blocks. So a plant, in the previous example, this is the car. You see, in order to be able to control the plant, we need to have some sort of input. This input is the way to influence the behavior of the plant. If you cannot influence the behavior, of course, you cannot control it. Right? So if you want to control the position of the car in the road, you need to have a wheel. So the wheel, the wheel position is that's input. Yeah, so that's input. Then you have kind of the desired, that some kind of concerned behavior right? The concerned behavior must be described by some kind of a variable, right? So that concerned behavior is called output. Output. So in the previous example, the output is the deviation of the car from the center of the road. The deviation. You want the deviation to be 0, basically. But of course, you cannot keep it exactly 0. You just want the deviation to be small, around the center line, roughly. So that's our output. In addition to the input-output, you may have some other, some other arrows going in, and some other arrows going out. So this arrow is called the arrow means a signal. Okay, so this arrow means a disturbance. The road condition, the uncertain road condition, that's a disturbance. Wind condition, the weather condition might be another disturbance, right? All this unexpected stuff. Disturbance is something you cannot do anything about. It's external. From external. You don't know when it happens. When it happens, you cannot stop it. Measurement. That's a thing going out. When you want to control some variable, so this is your concerned variable. Very often you say, okay, in order to control it, we need to observe that variable. We need to measure that variable. So that's why we need to know the information, right? We do feedback control. We need to know the information about this variable. But sometimes we cannot directly get it. We can only measure some kind of other variable, which might be different from that one. But you can get information about that one from this one. So then we call this a measurement. Measurement is a variable which can be sensed, which can be measured. You can build a sensor, sensor to measure. We often hear sensors, like a temperature sensor. In this room, we have temperature sensors, and we have speed sensors. Velocity sensors, all those sensors, we can measure variables in the system. If we know we build a lot of sensors, then we get a lot of information about the system. Of course, we turns out that we should be able to control this system better. Okay, now we have the plan here. Now, how do we connect the controller with the plant so to get a control system? This is a control system. You see, this feedback control system is a loop. We have a loop here. It goes like this. You have a plant here. You have a controller here. But the connection of controller and plant is through a signal going through this actuator, and also through this sensor. We call this like an input part. So this is the output part, or sense, and the feedback part. The controller needs to have some kind of actuator to manipulate the plant, to influence plant. So a typical actuator is a motor. Nowadays you have all kinds of motors. You have all kinds of you have a linear motor, rotational motor, all of these things. Why we have motors? Because usually the controller process electric signals. And computer, you have digital signals. You go through digital to analog conversion, then you get the analog signal, but this is an electric signal. But a plant, actually, you can have all kind of plants. But probably the most common plants are mechanical systems, like airplanes, like cars, like robots. You have something moving, you know. So how to influence the mechanical system? Usually, you know, you have to have a motor. So this motor convert an electric signal to like a kind of torque, kind of a force to drive the mechanical system. So that's why you have you need to have actuator. Also, a sensor here. What is the function of sensor? You know, you take this measured signal here, but this signal might be, again, a mechanical signal, like a speed, position. Or sometimes you have the temperature or pressure or whatever. All right? Then you need to convert it to an electric signal so that the controller is usually like electrical way. Nowadays it's used by a computer. So you need a sensor. You build all these things. Actually, you don't really actually build them. So usually this plant is built by something else, someone else. You don't build the plant. What do we do in control? We need to select those things, actuator and sensor. We need to design this. So our focus on the designing. Especially when we talk about the theory on control, our focus is here. Because how to select actuator and sensor is not a theoretical, it's not theory based. You just look at technology and look at what are available in the market, and then you buy them and put them there. But the theory, our theory, control theory, has a focus on the controller. You need to design this controller properly. Actually, you know, if you look at the control system as a you know, like a human body's control system. Controller is our brain, actually. We process signals and make decisions. So plant, you know, you can consider that just arms and our body, you know, we need to move in the right way. Sensor, we have a different sensory system, right? Like we can hear, we can see, we can smell, and all these things. Actuator, actually probably our muscles, you can consider as actuators. Also, our muscles here get like an instruction from our brain, right? Then we try to drive this the whole body to move in the right way. So, okay, stabilization. So that's a schematic diagram of stabilization. Put in a more formal way, you know, what is a stabilization problem? This is not really the final mathematical problem. This is just like a more